Alright, I wanted to go over a couple of problems I assigned for the chapter, no, it's really for the complex power homework. A couple of these problems actually came from chapter 11. Most of the work that we did in chapter 9 and chapter 10 was essentially that sinusoidal steady-state analysis. Chapter 11 is when we started talking about single-phase power, but I really wanted to tack on complex power basically into what we're going to be doing for test 1, just because all we're doing is just taking the voltages and the currents that we're actually finding within the circuit with sinusoidal steady-state analysis and then applying it to a concept of complex power. So we're going to review these couple of problems. It was 11.51, 11.54, and we're going to look at 11.57 as well. So let's just take a look at 11.51. Now for this one, we wanted to actually find the complex power from the source, or S source. So here everything was in RMS. All the problems are essentially in RMS for essentially all of chapter 11. But here we had basically a voltage source of 50 at an angle of 50 degrees, RMS, connected to a 2 ohm resistor, and then we had two parallel branches here in which we actually had an impedance of each. The first branch was 10 minus J5, that was the value for the capacitor, and also for the second branch 8, and then in series with that J6 inductor. Now remember here guys, we didn't actually have to do any of the conversions that into the impedance equivalents. They went ahead and did that for us. So in order to find the power from the source, we're just going to do this essentially the basic method of collapsing this down, finding the current, and then saying S is equal, or the complex power is equal to VRMS times IRMS conjugate. So we're going to find the equivalent impedance as we have done before. So 1 over the summation of the branch reciprocals. So in this case 1 over 10 minus J5 plus 1 over 8 plus J6. And that came out to be an equivalent impedance of both of those branches as basically being 6.154 plus J.77 ohms. What that means here, guys, is that even though we had a capacitor as well as an inductor, that positive value of reactance right here means that the equivalent branches together, their equivalent impedance, is more inductive in nature because of that positive sign right there. So now we have a single series loop. So here we have 50 at an angle of 50 degrees in series with 2, and then in series with this the equivalent impedance of 6.154 and then J.77. So we found the source current. We find the source current simply by saying 50 at an angle of 50 degrees over 8.154 plus J.77. And so when we did that, we come up with essentially, well, the conversion here would be 50 at an angle of 50 degrees over 8.19 at an angle of 5.4 degrees, and that came out to be a current of 6.105 at an angle of 44.61 degrees amps. So when we apply the concept of complex power, which obviously that's S is equal to VRMS times IRMS conjugate, then we get 50 at an angle of 50 degrees multiplied by 6.105 at an angle of 44.61 degrees. Now remember here, we got to conjugate that because that goes back to the instantaneous power and that theta V minus theta I. We have to stay consistent with that, so we have to conjugate that phase angle right there. I don't know why I delayed on that, but anyway, we have to conjugate that, which means that that becomes negative 44.61. And so in this case, guys, if we look, the complex power comes out to be equal to 152.63 at an angle of 5.4 degrees volt amperes. But that's in its polar form. When we convert this over into basically its rectangular form, we actually get the real power, P, 152.95 watts. And then the imaginary power, or what we call the reactive power, is 14.36 var. So the real power is actually going to be 152.95 watts, and then the reactive power is 14.36 var. essentially here, guys, this is pretty cool in a way, because what we're actually seeing here is that the positive reactive power is indicative of what we already know as being a mostly inductive circuit. And one thing I also want to make sure we all understand is that because it's an inductive current, that current needs to lag behind the voltage from the source. And sure enough, it does. It only lags just by a little bit. So here we get basically 6.105 at an angle of 44.61 degrees amps. That means that that current is lagging behind by a very, very small amount, essentially that 5.4 degrees behind that voltage of 50 at an angle of 50 degrees. So sure enough, we were able to not only prove out that this is definitely an inductive circuit. We can see that because the current lags behind that voltage by 5.4 degrees, but also that we actually come out with a positive reactive power because we do have a little bit of inductance in here. Now we're going to talk about efficiency within the circuit at a later point, but right here we actually can really see that this is going to be more of an efficient circuit because we have mostly resistance that we're going to be working with, a very, very small value of inductance. So we're at inductance. So if we look down here, we're actually not creating too much reactive power within the system, and that's really, really, really good. We want mostly real power to be absorbed within the system. And we're going to talk about power factor and what that means. Power factor is nothing more than talking about the efficiency of the system. And when theta V minus theta I become very, very close, that means it's acting more resistive in nature because the current and the voltage phase angles for a resistor are the exact same. And that means that we're getting all real power within that resistor. But more on that in just a bit. Let's take a look here at 11.54. Now with 11.54, this problem's kind of weird up front because usually we expect to have a voltage source that's in series with the resistances. But in this case, we actually have a current source. And so it's actually set up just for ease of calculation, I think. But one at an angle of 0 degrees, and basically they wanted us to find the complex power in this branch that was in series with that current source, the complex power in this branch that includes just one single capacitor, and then the complex power in the branch that contains only the 20 ohm resistor. Now one thing that is kind of weird about this problem is that when it does ask, or any problem asks for the complex power within any branch, normally we look at seeing that being made up of real and reactive power, P plus or minus JQ. However, when we look at a capacitor, even though we know that a capacitor will have only reactive power in it, we still have to say volt amperes in the event that they ask us for the complex power. Same thing for the resistor. We know that in a resistor, the only thing that we're going to have is real power because we're absorbing that energy. We're burning it up. So we still have to say, even though we know that's watts, if they ask for complex power in that branch and if it has only a resistor in it, then the only thing that we're going to need to put down is basically that complex power in terms of volt amperes. So let's take a look. Now because we have a current source here, that current's going to flow through 10 plus J10, and then get to the capacitor, get to the parallel resistor, and then split. So we can basically just use current division here. And the first part, we're just going to find the current in both branches. We already know the current that's actually in that series impedance up there. So Ix is equal to 1 at an angle of 0 degrees, and then multiplied by 20 over 20 minus J20. Don't forget the current division here. Opposite resistor goes in the numerator, and that comes out to give us a current here of 0.5 plus J0.5, and then convert it over into its polar equivalent, we get 0.707 at an angle of 45 degrees amps. For Iy, or the current flowing through the 20 ohm resistor, now we use the opposite branch, which is negative J20, and so we get Iy is equal to 1 at an angle of 0 degrees multiplied by negative J20 over 20 minus J20, and that's equal to 0.5 minus J0.5, which comes out to be 0.707 at an angle of negative 45 degrees amps. So let's take a look at the complex power. Now, there are several different variations that we could utilize for calculating complex power. If we just wanted to use current and impedance or voltage and impedance, we're going to look at the form in which we take the magnitude of the polar form of the current, square that, and then multiply it by the impedance. Makes everything pretty easy, especially because in this case we're looking at 1 at an angle of 0 degrees, amps as our source. So for S1, we're just going to take IRMS squared. So all we do is basically take that magnitude there, that's 1. Then we just square that. Doesn't need to include that phase angle because we're looking right here at magnitude. So the magnitude of basically a polar form is just 1 squared and then multiplied by that impedance in this branch right here, which is 10 plus J10, and that gave us a value of 10 plus J10 volt amperes, in which we had 10 watts, and then also the reactive power was actually 10 var. But total it's 10 plus J10 volt amperes. Let's take a look at this branch. Now, this one only contained the capacitor. We know that's only going to be reactive power. There's no resistance in there, so there's nothing that's actually really getting utilized. But for here, we have to answer the question in terms of volt amperes. So S squared is equal to IX. So we found that IX, the magnitude was 0.707, so it's 0.707 squared, and then multiplied by negative J20. And that came out to be equal to negative J10 volt amperes. However, we all know that we have basically 10 var within that capacitor. If we look down here, IY squared, that's going to be 0.707. See how that phase angle doesn't even come into play when we take the magnitude of it and square it? And we multiply it by 20 ohms, and that comes out to be equal simply to 10 volt amperes. But we know in this branch, since there's no imaginary portion to it, that we know that it's all real power, or 10 watts. But in this case, because they asked us for basically the complex power in that branch, then sure enough we have 10 volt amperes. Okay. Sometimes that confuses people because we know for the capacitor we only have reactive power, for the resistor we only have real power, but it's good to discuss that up front. But one thing I want to make sure everybody's very crystal clear on is that when we take the magnitude of any polar number, in this case for IX and IY, we were looking at 0.707 at an angle of 45 degrees. We only take the magnitude and square that. Okay. All right, let's take a look at another one now. Got to erase this, and you guys are going to have to just bear with me as I rewrite everything. It's not as efficient as if we were actually in the classroom, huh? All right. I don't have my eraser with me, so I'm using a hat. Guys are like, man, why am I having to watch a video of my instructor actually going through and erasing a whiteboard? Lame. Alright, so let's take a look at 11.56, not 57. And for this one, we actually want to find the power from the source again. Of course, we have 2 at an angle of 30 degrees, and that's going to be RMS. So for this one, if we wanted to find basically the complex power that's being supplied by the source and delivered basically to all of our impedances here, this one's super simple, because all we have to do is simply just, oh, we had a 6 ohm resistor right there, is basically just find the total equivalent impedance that the source would actually see, and then actually take the voltage that we would actually get from that. Oh, we also had 5 ohms right here, getting too excited. And then basically just go ahead and simply make our calculation of complex power. But I like this one because it gives you guys a little bit more experience with source transformation as well as equivalent impedance. For here, the equivalent impedance is just simply going to be equal to 1 over the summation of the reciprocals. So 1 over negative J2 plus 1 over 6. And that gave us a value here of 0.6 minus J 1.8. Alright, so let's perform source transformation over here, because when we do all these calculations, then we actually get the entire circuit into a single series equivalent. So here we're going to do source transformation, basically take 2 at an angle of 30 degrees, multiply it by 5. So then we get essentially 10 at an angle of 30 degrees. And then we take that 5 ohm resistor, we're going to put that in series. And when we reconnect that up to the rest of the circuit, then we get all elements now in series with each other. So 3, and then we got that inductor of J4. And then here with the equivalent impedance, we had 0.6. And then a capacitor, value of negative J 1.8. And so for now, all we have to do to find the power supplied from the source, in this case, S source would be equal to VRMS from the source, the magnitude squared, and then divided by ZEQ. Or basically the total impedance, which is just everything in series right here. And when we do that, we actually find that we get 10, because remember it's just the magnitude, we don't worry about that phase angle. 10 squared, and then we divide that simply by the summation of the impedances, 8.6 ohms plus J.22 ohms, and that we have to conjugate. Don't forget right here ZEQ, we have to conjugate that. I apparently didn't write that down. Here we got 10 squared over 8.6 plus J.22 conjugated, and then that comes out to be equal to 10.91 plus J 2.8 volt amperes. So let's talk about the impedance a little bit and a correlation to the current. Now, this is fantastic here, because here we see the other variation once again. We've seen this in another video of basically how we can easily just calculate that complex power. In this case, VRMS squared over ZEQ conjugate. In this case, we get that's equal to the magnitude squared over 8.6 plus J 2.2 conjugate. Now, obviously, with the polar form, we just negate whatever phase angle is there. In this case, this would actually become negative. So 8.6 minus J 2.2, and then that actually would give us a form of 10.91 plus J 2.8 volt amperes. And that makes sense here because the total impedance here was mostly inductive, and so we actually came out with a positive reactive power, which is consistent with what we should get with a mostly inductive nature reactance within the system. Now, let's just talk about ZEQ, and more importantly, why that 10 ohms that magnitude of the voltage source is just basically 10 volts squared. Why do we get rid of the phase angle? Let's look at something really quick. So we know that we have to be consistent with theta v minus theta I. We always have to be consistent with theta v minus theta I. And one thing that's really nice about the impedance is that the impedance conserves theta v minus theta I. Why? Well, let's just go back to the impedance variation of Ohm's law. Here V is equal to basically I Z. And so by that notion, guys, that I is equal, in this case, basically to Z is equal to V over I. And if we look at the polar form here, then that's equal to V at an angle of theta V over I at an angle of theta I. And when we divide those two together, we get the following. We get basically V over I at an angle of theta V minus theta I. So basically our complex power's phase angle is in fact actually conserved within that impedance. In this case, here if we did not conjugate that in the denominator, then we would actually not come out with theta v minus theta I. So we have to conjugate that. But it's important to remember here, guys, it's pretty cool that we don't need the phase angle right up here when we square that magnitude, because the phase angle of the complex power is already right here once we conjugate that and then divide through. Alright guys, so that should be some good information for those problems. If you have any questions about them, obviously come to discuss those in the meetings, or just get with me individually. Alright, see you later.